You know, back in algebra, when letters were involved in problems, we said that the letter is a variable. And we say that a letter in algebra is a variable because its value varies from problem to problem. X might be worth 5 in this problem on this equation, might be worth negative 68 over in this other equation. So it's a variable. Now, in statistics, we talk about randomness. We talk about chance. And so a lot of times variables take on the chance idea. And it's for that reason that variables are called random variables. For example, if we're talking about the sample space for rolling a die, then we're talking about the numbers 1, 2, 3, 4, 5, 6. Okay, so in getting one of those numbers, one of those x's, one of those variables, by virtue of rolling a die, we're taking a chance to identify the value of the variable. So it's a random variable. And that's all random variable means. There are two kinds of random variables that we're going to talk about. One is called discrete and the other continuous. Now remember, random variable is a numerical value which depends on chance. And that's all there is to it. It's the same kind of variable that we had in algebra, except if it depends on chance, it's called a random variable. Okay. Now, we're going to differentiate between discrete random variables and continuous random variables. And the reason we call attention to the difference here is because we're going to make some mathematical calculations, and the calculations are just a little different if we're talking about discrete random variables or continuous random variables, whatever that means right at this point. Let's talk about what that means. All right, discrete random variables simply means that they can keep a secret. Just kidding. No, discrete doesn't mean that they can keep a secret. It means that there are a countable number of them. Now, by countable, countable means something very special to mathematicians. Countable has a very particular definition. And let's just say that countable for our purposes means that the random variables, the number of random variables is finite, that is, it has a particular number associated with the total, or we can assign a counting mechanism to them. That is, we can assign counting numbers to them. It might be an infinite set, but at least we can go through the process of counting them. Now, some examples of discrete random variables might be something like this. Suppose we're thinking about choosing a person at random and deciding on or determining the number of hairs on their head, let's say. And so, although there are quite a number of them, it is a countable number of hairs on people's heads. So we have a discrete random variable, random because we're choosing the people at random, and it's discrete because we can actually count the number of hairs on a person's heads. Same way with animals. We could count the number of hairs. Even though there would be a lot of them, we can count them. And even if there were an infinite number of them, we can associate a number with a hair. You see, something like that. Now, contrast that with the notion of continuous. Continuous has to do with measurement. And that's actually why I put the word measure right here. Whenever you have a problem that has in it the word measure, then generally you're talking about a continuous random variable type of problem. If you're talking about the measures of students' heights in a class, and you're choosing students at random and you're talking about their heights, what values can those height measurements take on? Well, not only are they infinite, there are an infinite number of measures that are possible, but they're not even countable. We can't count the number of different measures that are possible. In fact, within the interval from 0 to 1 on a number line, there are an uncountable number of values if we're talking about real numbers, because you can give me a way to count them by saying, well, let's see, if we take all of the numbers and we go by 1/1000th each time, we'll have them all. No, we won't, because between 1/1000th and 2,000ths, we have loads of numbers. In fact, we have an uncountable number right there in that little interval. But because of the idea of having the infinitude of decimal places available to us for a distance from 0 to 1, we have this idea of uncountability. So not only are there an infinite number of numbers between 0 and 1, they're not even countable. So this continuous idea, this continuity of measurement, is what gives rise to the continuous random variable idea. Okay, so the continuous notion often involves the word measure. We could be measuring temperature, we could be measuring distance or heights or other items like that. But if we're counting items, then we're talking about discrete. So with continuous, we're talking countless or forming a continuous data set for this continuous random variable. Now we're not going to belabor the difference between these two and look at a lot of examples of each one and find it difficult to place things into one category or another. I'll tell you up front that in this section we're going to be talking about discrete random variables. And in a later chapter we're going to talk about continuous random variables. But it's important that we understand that there are two kinds at this point in time. Okay, so here we go with our discussion of discrete random variables. Now, in an earlier section, we had a chart. We were talking about the number of automobiles owned by families in a small town. And the chart went something like this. Number of cars owned, this is X, is 0 through 5. All right, and then we had a number of families associated with these various numbers of automobiles. And we found that the number of families in the city, because we're adding the frequency column, is 4,000. Now these values of X are discrete random variables. Now the discrete idea is that there are a countable number of them. There are 6 items in the X column, discrete. Now, random because these numbers, these X values are random because they depend upon which family is being selected at random. You see, if a family is selected at random, you see, how many of those families, or what's the probability, or we're asking questions like that. If a family is selected at random, let's talk about the number of automobiles that family has. Well, if the family is selected at random, then the variable associated with the number of cars is a random variable. All right, so we've belabored that point, I think, quite enough. Okay, when we had this discussion about frequency involved with this, we made a relative frequency column, and we talked about relative frequency and associated it a little bit with probability, and we want to really nail that right here in this segment. Relative frequency, the frequency with which 0 cars will occur is, let's see, relative frequency is the frequency divided by the total of the frequencies, the total n of items that are possible in the sample. So 17 over 4,000 would give that value. And let's see, for 2, it would be the frequency 1,767 divided by 4,000, and that's this number. So relative frequency. How relatively frequently will 2 occur in this random sampling process? Well, it will occur this relative frequently. Now, if we were talking about if a family is selected at random, what is the probability that that family will own 3 automobiles? What's the probability that that family will own 3 automobiles? Well, let's think favorable outcomes over possible outcomes. Favorable outcomes. Well, in all of these 4,000 families, this many of them, 1,107, own 3 automobiles. So favorable outcomes would be this many. Possible outcomes, we're going to 4,000 families to make this selection. So this number over that number, you see, would give the probability. So this relative frequency column is really just a probability column. We could call this a probability distribution if we want to, in dealing with these as probabilities rather than relative frequencies. And I think the point I'm trying to make here is that the notion of probability associated with a table like this, a frequency table, is not unknown to us. It's something that we just haven't named this way in the past. So what I could do right here, if we're talking about a probability distribution, I change this relative frequency column and just rename it. And I just name this, I could say this is probability that X will occur. You see, it's the probability that 1 will occur is right here. The probability that this X will occur is right here, and so on. Okay, so now it's a probability distribution. Okay, let's talk about what a probability distribution is. It is the assignment of probabilities to the various values of the random variable. Okay, so we have values of a random variable over here. Those values go from 0 to 6, and we are assigning probabilities to those various values. That's what a probability distribution is all about. Now, we kind of need that frequency column in order to determine the probability distribution. It's determined in exactly the same way as the frequency distribution was before. Now we're going to talk next about the notion of the calculation of mean and standard deviation. And let us limit ourselves or talk in terms of a population now rather than a sample. We talked in terms of samples quite a bit in the past. I want to talk in terms of population right now. Now, in terms of population, we're talking about mu for the mean and sigma for the standard deviation. Now, let's try to develop this in a way that differentiates or compares and contrasts with what we had talked about before when we discussed those ideas. So let's come back over here and do that. Now, you'll notice a lot of things I have on the board behind me. We'll get to those columns in just a little bit, but let's do them in sort of in order here. I want to talk about mean and standard deviation from what we discussed before. You know, before I do that, though, I think I'd better make sure we understand the notion of probabilities over here, this P of X. If we ask ourselves, what's the probability that a family selected at random will own 4 automobiles, then all we do is take 4 automobiles, here's the probability associated with that. The probability is 0.05. If we're saying what's the probability that the number of automobiles will be, let's say less than or equal to 2. Less than or equal to 2. That means 2, 1, or 0. And so we come over here and we would add these probabilities to get the probability that a family selected at random will have 2 or less than 2 automobiles in that family. Okay, that's the idea. Okay, now let's go back to our notion, our fundamental ideas for mean and standard deviation. If we're talking about a population, then the mean is noted like this. And recall that it's the sum of, if we're talking about a frequency distribution, which we had up here earlier before I changed that to P of X, then recall that it was the sum of X times F, and all of this is divided by N. And the sum of XF divided by N over here, now the sum of XF, we would have to come over here, and here's the X times F's. All right, now the X's are these, and the frequencies are these. And X times F, just the product of these two going across, would give this column. And the sum of that column is 8,692. All right, so we would come back over here, and it would be 8692 over N, the number of items is 4,000. And we find that that value is, I think it's an exact value, and it's 2.173. Okay, now, then the standard deviation, recall, was a little bit of a complicated kind of looking formula, and we could use the notion of SSX in that formula if we want to. And there was a little bit of a difference, a little nuance involved in whether we're talking about x bar, or excuse me, the standard deviation of a population or the standard deviation of a sample. And that difference had to do with dividing by either n or n minus 1. When we're talking about the population, we're dividing by n. But at any rate, I'm just combining everything here into one expression, and it turns out to be the sum of x squared f minus the sum of xf squared over n, all over, now if we were talking about a sample, this would be n minus 1, and this would be a little n. But here we're talking about a population, so it's big N. All right, and when we make this calculation, we need to get the sum of x squared f. Now the sum of xf's, we have the bottom of that column is over here. Let's go over and talk about those. We have, here's the xf column. We used this just a moment ago to find mu, the mean. Now here's x squared f. X squared f is found by squaring each of the x's and multiplying times the frequency. Okay, and we get all of this. Now here's the sum of the x squared f column, 21,908. All right, I made these columns because they're consistent with what we've done before. All right, let's come back over here and use that information in the formula. So we have, let's see, the square root of sum of x squared f, and I'm reading over there the sum of the x squared f column, 21,908. And then minus the sum of xf, the sum at the bottom of the xf column, 8692. And this value is squared. And this is over n is 4,000. And all of this is over 4,000. Now recall that, I better put this down here. Recall that there were variations on this formula. We could take the tactic of making the table according to the remember, most of the time we used samples, so we were talking x bar, but we had a column of x minus x bars, and we had x minus x bar squares. You see the sum of squared deviations and all of that kind of thing. So we went through that discussion before. But here was one of the shortcut formulas that we discussed. Now, when we punch this into the calculator and so forth, we find that this is approximately 0.87 for the standard deviation. All right, now it's important that we kind of recall 0.87 for the standard deviation and 2.173 for the mean, the population mean. The reason for going through this whole discussion is to compare the way that we made the calculation for mean and standard deviation here to a new way of making those calculations using the probability distribution idea. Let's come over here and talk about an alternative formula for calculating mean and standard deviation. The mean, mu, is only the sum of x times the probability of x. So it's just the bottom, the sum in that column of x probability x. And over here, if we come back this way, and I've got a column for x probability of x. Now, we're talking about probabilities over here, and we're making that discussion over here. All of this table is not important for us to produce every time we have a problem. It's kind of misleading in that way. We don't really need everything that we see here. Now, I'm going to just, I'm going to take out, see, we use these to figure that stuff over there. Let me take this out. Don't need it anymore. We're talking about a probability distribution now. And by the way, before I forget about it, what do you suppose the sum of these probabilities will be? See, it turns out that if you add all of the items here, The probability of, this is the probability that the family will have 0 cars, the probability that the family will have 1 car, the probability that the family will have 2 cars, and so on. And so if we add all of these, we should get 1, and we do indeed. You see, so we have an assignment of probability for every one of these variables, and the sum of those probabilities is 1. That's kind of an important aspect. Okay. Now, at this point in the problem, we really don't need the frequency numbers either. The frequency numbers were helpful for producing this column, but that's all. Okay, we can take these out. Now, we have the x times probability of x column. Now, and all I did is multiply, let's come back over here. All I did to produce that column was multiply this value times that value to get the top value over there. This value 1 times this to get the next value over there. 2 times 0.44175 gives 0.8835, so on. Okay. Now, the sum in this column, just add these rascals, we get 2.173. 2.173, where do I remember that? That was back over here. That was the mean of the population. That was mu. 2.173 then is the sum of the XPX column. You see, 2.173. So it's another way to make the calculation for the mean. Now the mean, when we're talking about probability distributions, is often referred to as expected value. Expected value. Now here's the formula for the calculation of the standard deviation. It's the square root of the sum of, now this is going to be a column, and it's the x minus mu, you see, x minus mean squared, times px, times the probability of each of the x's. Let's see how it's generated. We would generate a column of x minus mu. Now remember, mu is 2.173. So we take each x value. The first x value was 0. 0 minus 2.173 is negative 2.173. Then 1 minus 2.173 is minus 1.173, and so on. Remember what the sum of these would be? So the sum of all of these rascals turns out to be 0. At any rate, we then square these values. We can't use these values. Remember, we talked about why we can't, because some of them are negative, some of them are positive, so we just can't take an average of distances. These are distances from the mean is all it is, but they have kind of a direction associated with them with the positiveness and negativeness here. So we can't just take the average of those. So we square them. We make them all positive by squaring them. So square these and we get this column, the x minus mu squared column. And then we multiply these values times the probability of those values occurring. And so we have this column times the probability column, and we get all of these. And here's the sum of those. Now, this value is the value that turns out to go under the radical. So it's the 0.755 that's under the radical, and the square root of that gives approximately 0.87. So it's the values that we calculated here are consistent with the values that we calculated a different way earlier. What was the age distribution of nurses in Great Britain at the time of Florence Nightingale? Well, thanks to Florence Nightingale and the British Census of 1851, we have the following information, which we'll look at in just a moment. You might be interested to know that in 1851, there were over 25,000 nurses in Great Britain. Well, here's the distribution that we referred to. Notice the first column, the left column, is composed of age ranges, and in the next column the midpoint for all of those age ranges, and then a percent of nurses associated with each of these age ranges. Now, using the age midpoints x and the percent of nurses, do we have a valid probability distribution? Well, it turns out that we do, and we do because each random variable x falls into or has associated with it a distinct percent, and the percents add to 1, more or less. Now, there is a rounding error here, but it's at about the third digit to the right of the decimal, so it's negligible. But the answer is yes, because outcomes are distinct and probabilities total to 1. Use a histogram to graph the probability distribution of Part A. Well, let's see, a histogram. We want to make a histogram having to do with this information. So we would begin by structuring a coordinate plane, and the coordinate plane has a horizontal and vertical axis. Notice on the horizontal axis we'll list the age of nurses, those ages, and we're using midpoints for the various ranges. And on the vertical axis, we're writing probability values, and they're nothing more than the percents that appear in the third column. So P of X and percent of nurses correspond with one another. And then all we do is make a spot on the graph according to those percents, and our histogram is formed. Next, we want to find the probability that a British nurse selected at random in 1851 would be 60 years of age or older. Well, 60 years of age or older would put that nurse into one of these three categories. And those three categories have probability values or percents associated with them. All we need to do is add those percents, and we find that the probability that a British nurse selected at random would be 60 years of age or older would be almost 36%. Compute the expected age, mu, of a British nurse in 1851. The expected age, the mean age, you see, of a nurse in 1851. We have a formula associated with that idea. It's the sum of xpx, and it just means that we need to multiply the values in a couple of columns. Now, let us understand that the percent of nurses is just the px column, like this. And if we multiply the values in the middle column times the value in the third column, we'll have a column of xpx's. And here are those values. Then we add those, and we have the sum of xpx's. So the expected age, or the average age, the mean age of nurses, of a British nurse in 1851, is almost 54 years old. Next, we want to compute the standard deviation, sigma, for ages of nurses shown in the distribution. And as before, we have a formula associated with this calculation, and here's that formula. We know that in the past we got a lot of mileage out of arranging our columns in order to accommodate the information for the formula. Notice that the formula involves mu, or the mean value, and we calculated that earlier. It's kind of important to write that down or have that in mind when we make the columns that we're going to make. Now, the columns that are important to us have to do with x minus mu, or x minus the mean, and so we'll make a column for that purpose, and then the squares of those values would be x minus mu squared. And then if we take each of those items and multiply times px, we'll have the values that we add for the number that goes under the radical. And so we would just start out by saying, okay, what's the x minus mu? Well, for the first value, it would be 24.5 minus 53.76, and its value would be written down, and so on for all of the rest of them. And we've done this so many times before that we know how to make that calculation, I'm sure. And then squaring all of those entries, we would have the entries in the next column, and then multiply each of those by px, and we have this. And then we would add the entries in that column, and the sum of those entries is that sum that's listed under the radical. So we take the square root of this number, and we find that the standard deviation for ages of nurses shown in the distribution is 13.66 years. USA Today reported that about 25% of all state prison inmates released on parole become repeat offenders while on parole. Suppose the parole board is examining 5 prisoners up for parole. Let X equal the number of prisoners out of 5 on parole who become repeat offenders. Here is a probability distribution for X. Now let's understand how this distribution works. Now the number under the 0 is the probability associated with the idea that none of the 5 parolees will become repeat offenders. The number under the 3 is the probability associated with exactly 3 of the 5 parolees becoming repeat offenders. Let's answer some questions. The first one says, find the probability that 1 or more of the 5 parolees will be repeat offenders. So the probability that x is greater than or equal to 1 is what we're looking for. The direct approach to this problem is to say, well, let's see. The probability that x is greater than or equal to 1 is the probability that x equals 1 plus the probability that x equals 2 plus the probability that x is 3 and so on through adding the probability that x equals 5. And we can certainly add those values. We simply write them down and add them, and we find that probability to be 0.764. So there's actually if we put a percent to this, it's actually a little over 76% chance that 1 or more of the 5 parolees will become repeat offenders. There is another way to work this problem, and it's based on the idea that the sum of all of these probabilities is equal to 1. So the probability that x equals 0 plus the probability that x is greater than 0, that is, x is greater than or equal to 1, would be equal to 1. And so solving this for the probability that x is greater than or equal to 1 gives us the idea that we can solve this dilemma or find our answer as 1 minus the probability that x equals 0. Now the probability that x equals 0 is 0.237. 1 minus 0.237 is 0.763. The B part says, find the probability that 2 or more of the 5 parolees will be repeat offenders. Once again, there is a direct approach and a kind of an indirect approach. The direct approach works like this. The probability that x is greater than or equal to 2 is found by adding probabilities 2 through 5. That is, it's the probability that x is 2 plus the probability that x is 3 plus the probability that x is 4 plus the probability that x is 5. And adding, we get 0.368. The indirect approach is to calculate 1 minus the probability that x is less than 2. And we can do this because we know that the sum of all probabilities is equal to 1. Now the probability that x is less than 2 is equal to the probability that x equals 1 plus the probability that x equals 0. So adding those two probabilities and then subtracting that sum from 1 gives us 0.367. Now you might notice in these calculations that there is a single digit difference. That third digit to the right of the decimal is sometimes different from our previous calculation, and that's due to a rounding error, but it's an insignificant amount, so we say that the values are equal. C says find the probability that 4 or more of the 5 parolees will be repeat offenders. So we're finding the probability that 4 or 5, you see, will be repeat offenders, and we find the value by adding the probability that x equals 4 plus the probability that x equals 5. And we find that that probability is fairly low. It's 0.016. Suppose we want to compute mu, the expected number of repeat offenders out of 5. The expected number, the mean number, the average number. Different ways of saying pretty much the same thing. We have a formula associated with the idea. It's the sum of xpx's. So we would multiply each of these x values times the probability associated with them and add all of those products. And the calculation would look like this. So the expected number would be 1.25 of the parolees becoming repeat offenders. There's another way to set up this problem and its solution, and we've seen this way a little more often. It's to write columns for x and the probability of x, and then create a column for xpx. And then the problem then would look like this, and adding the values in the xpx column, we would get 1.25 1.253. Now notice the 3 is on, we talked about this average or expected value being 1.25 before, and here we have 1.253, and there's just a rounding difference in those two values, but we'll take them to be exactly the same. So this is the sum of the XPX values. Now we want to compute sigma, the standard deviation of the number of repeat offenders out of 5. And remember, the formula for that would involve x minus mu, and then x minus mu squared, and then x minus mu squared px as columns in our calculation. So we would go through and probably do this. We would create a column for x minus mu, and then write those values. Now remember, mu is 1.25, so that top value of negative 1.25 is found from thinking about 0 minus 1.25. So we get negative 1.25, and so on down the line. Then we want to square these values for this column, and then multiply each of these values times the probability associated with them to get the values in this column. Adding them, we have the number that appears under the radical, and then the square root of 0.938 is 0.968, and that is our standard deviation for the number of repeat offenders out of 5.